I heard once that Maxwell's equations are beautifully symmetric and that they prove light is an electromagnetic wave. Okay, so here they are. But where's the symmetry and where's the light wave? Well, that's what this video is about. First, a brief reintroduction to these four laws: Gauss, Faraday, and Ampere. Let's go across the top row first. Closed integral EdA equals the charge over the permittivity of free space, epsilon naught. This is where Coulomb's law comes from, counting up the field lines coming out of the surface. How about Gauss's law for magnetism? Closed integral BdA equals 0. Always 0? Yes, always, which explains the qualities of magnetic field lines. Next, Faraday's law. Closed integral EdL, a path integral, equals negative d phi b dt, the change in magnetic flux per time. This law shows how cutting a magnetic field line can induce a current. We already know about magnetic forces, the kind in electric motors. This law gives us electric generators as well. One more, last one, Ampere's law. Closed path integral of B equals mu, the permeability of space, times current. This law gives us the circling magnetic field lines around a wire, as well as the field of an electromagnet. They are nice, but there's something missing. These are the equations Maxwell inherited, but he tweaked them, specifically this one. There's something missing, Ampere. Well, let's take a look at a basic circuit. Magnetic field around the wires. Okay, but let's put in a capacitor. True, this will be a short-lived circuit. The capacitor will quickly fill up with charge and current will go to 0, but we're focusing on the magnetic field and the space between the capacitor plates. There's no current there. Will there be a magnetic field? Well, there kinda is a current. As the positive plate fills up with charge, the electric field between the plates increases in strength, and we can work out the details mathematically. There might not be moving electrons, but there is a changing electric field. Distance cancels out. The electric flux is the field strength times area. Next, divide by T. Oh, that's current, isn't it? Charge per time is current, and it equals epsilon naught times d phi e dt. Somebody needs to tell Ampere about this. He was only interested in the currents in wires, not the changing electric fluxes in space. But those changing fluxes, you could call it a displacement current, these changing fluxes also create circling magnetic fields, so no holes in the magnetic field. And the equations are tweaked. Nice. But still not very symmetric. But they would be in a vacuum. No Q, no I, no Gauss, and the bottom two are looking pretty snappy. So a changing magnetic field produces an electric field, and a changing electric field produces a magnetic field, the electromagnetic wave. So our challenge now is to show that this wave travels at the observed speed of light. First, let's take a closer look. The magnetic and electric fields are in phase, and this shows here a continuous wave, a steady light source. But you could also imagine a single photon or a pulse. Think of the crowd doing the wave, only in 2 dimensions. To continue with this proof, let's use a box. Now this one has 6 faces. They all have 6 faces, 2 each in 3 dimensions. Here, the electric field intersects the top and the bottom faces. The magnetic field points front and back, and the wave itself is moving left to right. We'll put the box here, where both the fields are at max strength. And also, we don't really care about the entire box, just 2 faces, just these 2 squares, the bottom square and the back square. And we'll consider the back first. Imagine a photon that's going left to right, just reaching the left edge of this square, meaning that these are the only 2 field lines that we'll need to worry about. Bring in the equations, especially this one, Faraday's law. And with the wave's arrival, we should have a changing magnetic flux. First step is to find the distance it travels in a small time dt. That will give us the area which the magnetic field pushes through. Nicely. That area times magnetic field is magnetic flux. Substitute. Rearrange. And we have an expression for d phi b dt, the change in magnetic flux per time. Faraday can take it from here. But what is integral EdL? This is. Only one side of the square feels the electric field. E acts over distance A. But why negative? Well, it's because of the counterclockwise convention. E dot L is clockwise. See that? Good, because we're done. Done with Faraday, half done with the proof. We'll put this cute little expression aside for later and turn our attention to the blue bottom square and to Ampere's law. Second verse, same as the first. Again, the wave is just arriving at the left of the square. So these two field lines are the only ones we need to worry about. And this is the area through which the electric field points. Distance equals c dt, the area of a rectangle. Substitution. Definition of flux. Substitution again. Change in flux. Now, Ampere's law. Looking good. Pop quiz. What is B dot L, or integral B dot dl? It's B times A. Counterclockwise around the square this time. Positive. And there's our second equation. Nice how A cancels out. The size of the box should not matter. Now, let's get these guys together and substitute and solve for C. This is what we wanted, an expression for the speed of our electromagnetic wave in terms of known constants, mu naught and epsilon naught. A small note here, since I first worked out this stuff, the definition of mu naught, the permeability of free space, has changed somewhat, not too much, but a little bit, which makes this out of date anyway. We have what we want. Work out the details, work out the math, do the calculate. It's 3 times 10 to the 8th, the speed of light, the measured speed of light. And there you have it, from Maxwell's equations to the speed of light. That is after Maxwell tweaked Ampere and threw him out into space. Oh, it's a good thing. Light can travel in a vacuum.